Spaceflight is ballistic flight into or through outer space. Spaceflight can occur with spacecraft with or without humans on board. Examples of human spaceflight include the U.S. Apollo moon landing and space shuttle programs and the Russian Soyuz program, as well as the ongoing International Space Station. Examples of unmanned spaceflight include space probes that leave Earth orbit, as well as satellites in orbit around Earth, such as communications satellites. These operate either by telerobotic control or are fully autonomous. Spaceflight is used in space exploration, and also in commercial activities like space tourism and satellite telecommunications. Additional non-commercial uses of spaceflight include space observatories, reconnaissance satellites and other Earth observation satellites. A spaceflight typically begins with a rocket launch, which provides the initial thrust to overcome the force of gravity and propels the spacecraft from the surface of the Earth. Once in space, the motion of a spacecraft, both when unpropelled and when under propulsion, is covered by the area of study called astrodynamics. Some spacecraft remain in space indefinitely, some disintegrate during atmospheric re-entry, and others reach a planetary or lunar surface for landing or impact. History. The first theoretical proposal of space travel using rockets was published by Scottish astronomer and mathematician William Leach, in an 1861 essay, A Journey Through Space. More well known as Konstantin Tsiolkovsky's work, published in 1903. Spaceflight became an engineering possibility with the work of Robert H. Goddard's publication in 1919 of his paper, A Method of Reaching Extreme Altitudes. His application of the de Laval nozzle to liquid fuel rockets improved efficiency enough for interplanetary travel to become possible. He also proved in a laboratory that rockets would work in the vacuum of space. Nonetheless, his work was not taken seriously by the public. His attempt to secure an army contract for a rocket-propelled weapon in the First World War was defeated by the November 11, 1918 armistice with Germany. Nonetheless, Goddard's paper was highly influential on Hermann Oberth, who in turn influenced Wernher von Braun. Von Braun became the first to produce modern rockets as guided weapons, employed by Adolf Hitler. Von Braun's V-2 was the first rocket to reach space, at an altitude of 189 kilometers on a June 1944 test flight. Tsiolkovsky's rocketry work was not fully appreciated in his lifetime, but he influenced Sergei Korolev, who became the Soviet Union's chief rocket designer under Joseph Stalin, to develop intercontinental ballistic missiles to carry nuclear weapons as a countermeasure to United States bomber planes. Derivatives of Korolev's R-7 Semyorka missiles were used to launch the world's first artificial Earth satellite, Sputnik 1, on October 4, 1957, and later the first human to orbit the Earth, Yuri Gagarin in Vostok 1, on April 12, 1961. At the end of World War II, von Braun and most of his rocket team surrendered to the United States, and were expatriated to work on American missiles at what became the Army Ballistic Missile Agency. This work on missiles such as Juno I and Atlas enabled launch of the first U.S. satellite Explorer 1 on February 1, 1958. And the first American in orbit, John Glenn in Friendship 7 on February 20, 1962. As director of the Marshall Space Flight Center, von Braun oversaw development of a larger class of rocket called Saturn, which allowed the U.S. to send the first two humans, Neil Armstrong and Buzz Aldrin, to the Moon and back on Apollo 11 in July 1969. Phases. Launch rockets are the only means currently capable of reaching orbit or beyond. Other non-rocket space launch technologies have yet to be built, or remain short of orbital speeds. A rocket launch for a spaceflight usually starts from a spaceport, which may be equipped with launch complexes and launch pads for vertical rocket launches, and runways for takeoff and landing of carrier airplanes and winged spacecraft. Spaceports are situated well away from human habitation for noise and safety reasons. ICBMs have various special launching facilities. A launch is often restricted to certain launch windows. These windows depend upon the position of celestial bodies and orbits relative to the launch site. The biggest influence is often the rotation of the Earth itself. Once launched, orbits are normally located within relatively constant flat planes at a fixed angle to the axis of the Earth, and the Earth rotates within this orbit. A launch pad is a fixed structure designed to dispatch airborne vehicles. It generally consists of a launch tower and flame trench. It is surrounded by equipment used to erect, fuel, and maintain launch vehicles. Reaching space. The most commonly used definition of outer space is everything beyond the Kármán line, which is 100 kilometers above the Earth's surface. In altitude, rockets are the only currently practical means of reaching space. Conventional airplane engines cannot reach space due to the lack of oxygen. Rocket engines expel propellant to provide forward thrust that generates enough delta-V to reach orbit. For manned launch systems, launch escape systems are frequently fitted to allow astronauts to escape in the case of catastrophic failures. Alternatives. Many ways to reach space other than rockets have been proposed. Ideas such as the space elevator and momentum exchange tethers like rotavators or sky hooks required new materials much stronger than any currently known. Electromagnetic launches such as launch loops might be feasible with current technology. Other ideas include rocket-assisted aircraft, spaceplanes such as reaction engines, Skylon, scramjet-powered spaceplanes, and RBCC-powered spaceplanes. Gun launch has been proposed for cargo. Leaving orbit. Achieving a closed orbit is not essential to lunar and interplanetary voyages. Early Russian space vehicles successfully achieved very high altitudes without going into orbit. NASA considered launching Apollo missions directly into lunar trajectories but adopted the strategy of first entering a temporary parking orbit and then performing a separate burn several orbits later onto a lunar trajectory. This costs additional propellant because the parking orbit perigee must be high enough to prevent re-entry, while direct injection can have an arbitrarily low perigee because it will never be reached. However, the parking orbit approach greatly simplified Apollo mission planning in several important ways. It substantially widened the allowable launch windows, increasing the chance of a successful launch despite minor technical problems during the countdown. The parking orbit was a stable mission plateau that gave the crew and controllers several hours to thoroughly check out the spacecraft after the stresses of launch. Before committing it to a long lunar flight, the crew could quickly return to Earth if necessary, or an alternate Earth orbital mission could be conducted. The parking orbit also enabled translunar trajectories that avoided the densest parts of the Van Allen radiation belts. Apollo missions minimize the performance penalty of the parking orbit by keeping its altitude as low as possible. For example, Apollo 15 used an unusually low parking orbit of 92.5 nmi by 91.5 nmi where there was significant atmospheric drag, but it was partially overcome by continuous venting of hydrogen from the third stage of the Saturn V, and was in any event tolerable for the short stay. Robotic missions do not require an abort capability or radiation minimization, and because modern launchers routinely meet instantaneous launch windows, space probes to the Moon and other planets generally use direct injection to maximize performance. Although some might coast briefly during the launch sequence, they do not complete one or more full parking orbits before the burn that injects them onto an Earth escape trajectory. Note that the escape velocity from a celestial body decreases with altitude above that body. However, it is more fuel efficient for a craft to burn its fuel as close to the ground as possible. See Oberth effect and reference. This is another way to explain the performance penalty associated with establishing the safe perigee of a parking orbit. Plans for future crewed interplanetary spaceflight missions often include final vehicle assembly in Earth orbit, such as NASA's Project Orion and Russia's Clipper Param tandem. Astrodynamics Astrodynamics is the study of spacecraft trajectories, particularly as they relate to gravitational and propulsion effects. Astrodynamics allows for a spacecraft to arrive at its destination at the correct time without excessive propellant use. An orbital maneuvering system may be needed to maintain or change orbits. Transfer energy. The term transfer energy means the total amount of energy imparted by a rocket stage to its payload. This can be the energy imparted by a first stage of a launch vehicle to an upper stage plus payload, or by an upper stage or spacecraft kick motor to a spacecraft. Re-entry vehicles in orbit have large amounts of kinetic energy. This energy must be discarded if the vehicle is to land safely without vaporizing in the atmosphere. Typically, this process requires special methods to protect against aerodynamic heating. The theory behind re-entry was developed by Harry Julian Allen. Based on this theory, re-entry vehicles present blunt shapes to the atmosphere for re-entry. Blunt shapes mean that less than 1% of the kinetic energy ends up as heat that reaches the vehicle, and the heat energy instead ends up in the atmosphere. Landing. The Mercury, Gemini, and Apollo capsules all splashed down in the sea. These capsules were designed to land at relatively slow speeds. Russian capsules for Soyuz make use of braking rockets as were designed to touch down on land. The Space Shuttle and Buran glide to a touchdown at high speed. Recovery. After a successful landing, the spacecraft, its occupants and cargo can be recovered. In some cases, recovery has occurred before landing. While a spacecraft is still descending on its parachute, it can be snagged by a specially designed aircraft. This mid-air retrieval technique was used to recover the film canisters from the Corona spy satellites. Types. Unmanned spaceflight is all spaceflight activity without a necessary human presence in space. This includes all space probes, satellites and robotic spacecraft and missions. Unmanned spaceflight is the opposite of manned spaceflight, which is usually called human spaceflight. Subcategories of unmanned spaceflight are robotic spacecraft and robotic space missions. A robotic spacecraft is an unmanned spacecraft with no humans on board, that is usually under telerobotic control. A robotic spacecraft designed to make scientific research measurements is often called a space probe. Unmanned space missions use remote-controlled spacecraft. The first unmanned space mission was Sputnik I, launched October 4, 1957 to orbit the Earth. Space missions where animals but no humans are on board are considered unmanned missions. Benefits. Many space missions are more suited to telerobotic rather than crewed operation, due to lower cost and lower risk factors. In addition, some planetary destinations such as Venus or the vicinity of Jupiter are too hostile for human survival given current technology. Outer planets such as Saturn, Uranus, and Neptune are too distant to reach with current crewed spaceflight technology, so telerobotic probes are the only way to explore them. Telerobotics also allows exploration of regions that are vulnerable to contamination by Earth microorganisms since spacecraft can be sterilized. Humans cannot be sterilized in the same way as a spaceship, as they coexist with numerous microorganisms. And these microorganisms are also hard to contain within a spaceship or spacesuit. Telepresence. Telerobotics becomes telepresence when the time delay is short enough to permit control of the spacecraft in close to real time by humans. Even the 2 seconds light speed delay for the Moon is too far away for telepresence exploration from Earth. The L1 and L2 positions permit 400 milliseconds round-trip delays, which is just close enough for telepresence operation. Telepresence has also been suggested as a way to repair satellites in Earth orbit from Earth. The Exploration Telerobotics Symposium in 2012 explored this and other topics. The first human spaceflight was Vostok 1 on April 12, 1961, on which cosmonaut Yuri Gagarin of the USSR made one orbit around the Earth. In official Soviet documents, there is no mention of the fact that Gagarin parachuted the final 7 miles. The international rules for aviation records stated that the pilot remains in his craft from launch to landing. This rule, if applied, would have disqualified Gagarin's spaceflight. Currently, the only spacecraft regularly used for human spaceflight are the Russian Soyuz spacecraft and the Chinese Shenzhou spacecraft. The U.S. Space Shuttle fleet has been retired. SpaceShipOne has conducted 2 human suborbital spaceflights. Suborbital. On a suborbital spaceflight, the spacecraft reaches space and then returns to the atmosphere after following a ballistic trajectory. This is usually because of insufficient specific orbital energy, in which case a suborbital flight will last only a few minutes. But it is also possible for an object with enough energy for an orbit to have a trajectory that intersects the Earth's atmosphere, sometimes after many hours. Pioneer 1 was NASA's first space probe intended to reach the Moon. A partial failure caused it to instead follow a suborbital trajectory to an altitude of 113,854 kilometers before re-entering the Earth's atmosphere, 43 hours after launch. The most generally recognized boundary of space is the Kármán line 100 kilometers above sea level. Above sea level, it is not generally recognized by the public that the increase in potential energy required to pass the Kármán line is only about 3% of the orbital energy required by the lowest possible Earth orbit. In other words, it is far easier to reach space than to stay there. On May 17, 2004, civilian space exploration team launched the Go Fast rocket on a suborbital flight, the first amateur space flight. On June 21, 2004, SpaceShipOne was used for the first privately funded human space flight. Point-to-point suborbital spaceflight is a category of spaceflight in which a spacecraft uses a suborbital flight for transportation. This can provide a 2-hour trip from London to Sydney, which would be much faster than what is currently over a 20-hour flight. Today, no company offers this type of spaceflight for transportation. However, Virgin Galactic has plans for a spaceplane called Spaceship 3, which could offer this service in the future. Suborbital spaceflight over an intercontinental distance requires a vehicle velocity that is only a little lower than the velocity required to reach low Earth orbit. If rockets are used, the size of the rocket relative to the payload is similar to an intercontinental ballistic missile. Any intercontinental spaceflight has to surmount problems of heating during atmosphere re-entry that are nearly as large as those faced by orbital spaceflight. A minimal orbital spaceflight requires much higher velocities than a minimal suborbital flight, and so it is technologically much more challenging to achieve. To achieve orbital spaceflight, the tangential velocity around the Earth is as important as altitude. In order to perform a stable and lasting flight in space, the spacecraft must reach the minimal orbital speed required for a closed orbit. Interplanetary travel is travel between planets within a single planetary system. In practice, the use of the term is confined to travel between the planets of our solar system. Interstellar 5 spacecraft are currently leaving the solar system on escape trajectories. The one farthest from the Sun is Voyager 1, which is more than 100 astronomical units distant and is moving at 3.6 astronomical units per year. In comparison, Proxima Centauri, the closest star other than the Sun, is 267,000 astronomical units distant. It will take Voyager 1 over 74,000 years to reach this distance. Vehicle designs using other techniques, such as nuclear pulse propulsion, are likely to be able to reach the nearest star significantly faster. Another possibility that could allow for human interstellar spaceflight is to make use of time dilation, as this would make it possible for passengers in a fast-moving vehicle to travel further into the future while aging very little, in that their great speed slows down the rate of passage of onboard time. However, attaining such high speeds would still require the use of some new, advanced method of propulsion. Intergalactic travel involves spaceflight between galaxies, and is considered much more technologically demanding than even interstellar travel, and by current engineering terms, is considered science fiction.